All right, let's see what I can do here. I'd like to look at constructing an orthogonal matrix. All right, so let's say I've got a matrix. Let's see, what should I call my matrix? I'll call my matrix M. So matrix M. And M will look like 1, 4, 4, 1. Excuse me if I'm using different notation. It's been a little while since I've made these, so the notation might be slightly different from what I was doing previously. And I would like to find an orthogonal matrix from its eigenvalues. Okay, so let's see here. How does this work? Well, first, probably I should remind you what an orthogonal matrix is. An orthogonal matrix is a matrix whose transpose is equal to its inverse. All right? That's sort of the definition. And then I just have to sort of find it. And the way we do that is, first we find the eigenvalues, right? So we have to find the orthogonal matrix from the eigenvalues. And then we just use those eigenvalues as column vectors in the matrix. That's really it. So first we'll find the eigenvalues. And we find eigenvalues using this characteristic equation, which is this element, this 0, 0 element minus lambda, and then nothing to this 0, 1 element, and the 0, 1 element, and the 1, 0 element still 4, and then the 1, 1 element, 1 minus lambda. So basically we've taken m and subtracted lambda times I, and then we're taking the determinant of that. All right, and we do this, we have 1 minus lambda squared, and this is going to be minus 16, right? So that's going to equal lambda squared minus 2 lambda minus 16 plus 1 is minus 15, and that's equal to what? Lambda minus 5 times lambda plus 3, they told me in junior high, and that's going to be equal to 0. All right, so that's going to give us our eigenvalues, and our eigenvalues are what makes this equal to 0. So if lambda is equal to 5, then this is 0 times whatever that is, that's 0. If lambda is equal to minus 3, this is 0 times whatever that is, that's 0. So those are my eigenvalues. Lambda equals minus 3 and 5. All right? So from those, we want to find the eigenvectors, right? So the eigenvectors we're going to find just by using the definition of an eigenvalue. Let's see, so how did that work? We had A, let's start with lambda equals minus 3, right? So an eigenvalue will be something where if you multiply a matrix by some vector, it's going to be equal to that eigenvalue times that vector. Okay? So this gives us two equations. We're really only going to need one of them. So that's like A plus 4B equals minus 3A, right? And that's actually enough for what we need to do. That's 4A plus 4B is equal to 0, right? Which means A is equal to minus B. So we can have a nice, let's go ahead and use a normalized eigenvector. So that first eigenvector is going to be, let's use V, 1 over the square root of 2. If A is 1, then B is minus 1. right? So we can go ahead with that and do this for lambda equals 5, right? And so we take that original matrix, multiply it by A and B. The eigenvalue is 5 now times AB, which means that A plus 4B is equal to 5A, which means that minus 4A plus 4B is equal to 0, which means that A is equal to B. So we'll have some vector W is equal to 1 over the square root of 2, 1, 1. Again, it's normalized, that's why I use 1 over the square root of 2. I think that's sort of sufficient. And then we need to construct the matrix. And like I said previously, when we construct this matrix, all we have to do is use these two vectors as columns, right? So what should I call this? Let's just say we call it n, and we use 1 over the square root of 2 times 1 times minus 1 and 1 and 1, right? V and W. So that's the matrix, right? The only thing we might want to do is actually check, right? It's usually good to check something. So let's check. Okay, so let's see. What is M transpose? M transpose is, let's see. Oh, not M transpose. We want N transpose because it's the orthogonal matrix. N transpose is just 1, 1, and then we flip these two around, 1 minus 1. All right. So that's the transpose. And to find n to the minus 1, we'll have to use some sort of technique. Let's find it using the I forgot the name of this method, so we'll just use the method that I can think of off the top of my head. So I've got 1, 1, minus 1, minus 1, and 1, 0, 1, 0. All right, and I'll just multiply that all by 1 over the square root of 2. That's going to go to, let's see, if I add this to this, I have 1, 1, 1, 0, because I'm not doing anything to the top row. And 1 plus minus 1 is 0, and 1 plus 1 is 2, and 1 plus 0 is 1, and 0 plus 1 is 1. All right. And then I'll go ahead and I'll reduce that, right? I'll say, okay, all I care about is this 0, 1, right? So I can pull out the 2, right? I think I can pull out a 2. And I have, I hope, a square root of 2, and 1, 1, 0, 1, and 1, 0, 1 half, 1 half, right? And then I can go ahead and, how close am I to the edge? I'm near the edge. All right, so I'll go down here. I can go ahead and subtract row 2 from row 1, right? So I have 0 minus 1 is 1, or 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 half is 1 half. 0 minus 1 half is minus 1 half. Then I just repeat all this stuff over here. I forgot my square root of 2. And I have a 0, 1 here, and a 1 half, 1 half. All right, now I'm going to factor in that square root of 2, right? So that I have square root of 2, 0, 1 over the square root of 2, 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 and that's awesome. My n to the minus 1 is 1 over the square root of 2, 1, 1, minus 1, 1. So that all works out. It's exactly what we thought it would be, which is a orthogonal matrix. All right, well, Thank you very much. I hope that's illuminating. I hope that helps you with your homework. All right, bye now.